In a previous video, we have reviewed a characterization of tangent lines to a circle on the Euclidean plane. Let's recall the statement of that characterization. It says that a line is tangent to a circle if and only if it is perpendicular to a diameter of the circle at an endpoint of the diameter. In this video, we're going to look at a generalization of this characterization, and it is called the tangent chord angle theorem. So from the title of this theorem, we could see that it is talking about a relation between a tangent line and a chord of the circle and the angle formed by those two lines or line segment. Let's look at the statement of this theorem. It says that if a line AB is tangent to the circle, which is denoted by C of O, OA, where O is the center of the circle and OA is standing for a radius of the circle. And the tangent line is tangent to the circle at point A, and if AC is a chord such that the measure of the arc APC is equal to x degrees, then we conclude that the measure of the angle formed by BAC is a angle whose measure is equal to 1/2 of the measure of the arc MPC. Well, to understand that this theorem is a generalization of the characterization of the tangent line, let's look at the first figure below. Now in this figure here, the line AB is a tangent line to the circle, tangent at point A, with the point of tangency at point A. And if we assume that the chord AC to be a diameter of this circle, then from the characterization theorem, we do know that the angle BAC is in fact a right angle, in other words, 90 degrees. On the other hand, we also observe that the chord is intercepting the circle at a semicircle, which is this APC over there. So when the arc happens to be a semicircle, the measure of this arc would be equal to 180 degree. So 1/2 of 180 degree is precisely 90 degree. Hence, the tangent chord angle theorem could be specialized to this specific case in which the chord happens to be a diameter. Now, in general, what we are trying to prove is that even if this chord is not a diameter, the relation between the angle BAC and the arc APC would still satisfy the condition that the angle is equal to 1/2 of the measure of the arc. And that is what we are trying to prove. Now let's look at the proof of this theorem. It turns out the proof is based on the characterization of the tangent line. So we would be considering the following two situations. In the first scenario, the arc APC is a minor arc, as what we are seeing on the figure, in the figure on the left. And on the other hand, we will be considering the second scenario in which the arc APC is a major arc, namely it's an arc that is greater than a semicircle. Well, the proof of these two scenarios turns out to be rather similar. So let's try to look at the idea over here. Well, as we have mentioned, it turns out to be based on the characterization theorem. So for instance, let's look at the figure on the left-hand side. And In fact, what we're going to do is going to draw the diameter through points A. And for instance, we could denote the other endpoint of this diameter as capital D. Well, similarly, we could also draw a diameter through point A for the second scenario. Well, in both of these two cases, we do know that the angle, the measure of the angle BAD is 90 degrees for both cases. Now, with this at hand, we could go ahead to do the following deduction. Observe that the angle BAC is in fact equal to the difference of the angle BAD and the angle CAD. Well, on the other hand, what we have learned from the characterization of tangent line is that the angle BAD is precisely 90 degrees, while the angle CAD, which is an inscribed angle of the circle, is going to be of the same measure as 1/2 of the arc. So for the sake of reference, we're going to put a point down there as Q. So the arc CQD is referring to the arc intercepted by this inscribed angle CAD. Okay, what we're going to do is going to observe that if we pull the 1/2 out, then what we are left with is going to be the difference between 180 degrees and the measure of CQD. But note that 180 degrees is precisely the measure of a semicircle, and since AD is a diameter, so the arc APD is precisely a semicircle. So the measure of this arc is equals to 180. So we could replace the 180 by the measure of this APD arc. Well, but when we refer to this diagram up here, we observe that if we take the arc CQD away from the semicircle APD, then what we're left with is precisely the arc APC. And this relation is exactly what we want to prove. In this condition, in this case. Now, to finish up the proof, let's look at the second scenario in which the arc APC is a major arc. The idea is quite similar. However, instead of expressing the angle BAC as the difference between two angles, we're going to observe that in this case, this angle BAC is the sum of two angles, which is the angle BAD and the angle ADC. Now again, for the sake of convenience, we're gonna pick a point in between CD and denote that as Q. So we could observe that those two angles, the measure of those two angles, are respectively equal to 90 degrees and 1/2 of the measure of DQC. And with the same trick, like what we have done in the last circumstance, we could pull out the 1/2 and then replace the 180 degrees by the measure of the semicircle APD. Now at this point, it's clear that the sum of those two measures, the sum of those two arcs, turns out to be the whole arc APC. Hence, we again conclude that the measure of the angle BAC is equal to 1/2 of the measure of the arc APC. And the proof complete.